we talked about what a function is, and we talked about x and y intercepts. So now let's take a look at another real life scenario. Sometimes Russell and I like to share some snacks. Obviously, these are the snacks that Russell could eat, but like he loves apple slices. So, for example, if I were to have 5 thin apple slices, every time I get about 5, he will get 1 thin slice of apple. So again, let's use our variables to set up our function. Let x be, I don't know, the number of apple slices that Russell eats, and let y be the number of apple slices that Lauren eats. Once we set that up, what you're going to notice is that intuitively, you're going to set our function to be y equals 5x. That's interesting because that 5, where does it come from? If you really think about it, this 5 represents ratio or rate. And by the way, rate is essentially ratio, but with different units. So for example, when we want to set up a ratio, for example, if I were comparing, because ratio is comparison of 2 values, right? So let's say if I were to compare my weight to Russell's weight, I would want to make sure that both are actually talking about weight, right? Like I cannot compare my weight to all of a sudden Russell's body length. It would have to be Russell's weight, right? If we're talking about weight. So that's how we can form a ratio and compare my weight to Russell's weight. However, if I were to take a look at a ratio with different units, so for example, like kilometers per hour, that is actually a ratio, right? You're comparing how many kilometers you could travel in 1 hour, correct? Now, we call this kind of ratio rate. So rate is usually, I wouldn't say usually, but rate oftentimes refer to like speed, right? Or how fast you get certain things done. But rate actually is just another form of ratio, but that compares different units. Anyway, that was a little side piece on ratio and rate, but let's get back to our little situation with Russell. So we have y equals 5x, and this 5 essentially represents ratio, right? Or rate between, well, in this case, it would be more of ratio because we're talking about the number of apple slices for both Russell and Lauren. So for every 5 apple slices that Lauren eats, Russell gets 1. So here, this is our ratio, and our ratio is right there in our function. And our 5 actually appears in our function as a coefficient. Coefficient is a number that is multiplied, numerical value that's multiplied to a variable. So 5 is our coefficient, but it also represents our rate. And this rate, in terms of linear function, is commonly known as slope. So how do we find our slope? Our slope can be found using the infamous rise over run. And essentially what rise over run means is we are comparing the difference between the y values, so the output values, we're comparing that to the difference between our input values, our x values, essentially. So slope is actually talking about rate, and rate is essentially ratio. So let's go ahead, try graphing it. If we try graphing it, what you'll realize is that it actually intersects our origin in the coordinate plane. Our origin is 0, 0, what I like to call the belly button of the coordinate plane. And this is because we have 0 as our y-intercept. Another important observation we could make is that our graph is increasing from left to right. It's going up. And that's really interesting because take a look at our slope. Our slope value is positive, right? So we know that when our slope is positive, that means our graph is increasing. So we have this graph that's increasing, that intersects at the origin because its y-intercept is 0 and its x-intercept is also 0. We call function model like this direct variation. When we have direct variation, it simply means as our input value goes up, our output value also goes up. Likewise, if our input value goes down, our output value also goes down. And there is no x or y. Well, we do have x and y intercept, but there are 0. So a graph model of direct variation would always intersect with the origin. Let's go ahead, switch our perspective a little bit. Instead of looking at the number of apple slices that Russell get as my input value, I'm going to go ahead and look at Lauren's apple slices as my domain. What I end up getting is y equals 1 over 5 times x. So my slope has been switched. Let's go ahead, graph this. Compared to the graph that we just had, you can see that our slope is a little bit flatter, right? It's not as steep, correct? So now we know that as our slope value gets bigger, the steeper it becomes. Why? Because our rate of change is greater. So still, we have a positive slope, so therefore our graph is increasing more or less, but it's not increasing as dramatically, right? Okay. What if we look at it from the perspective of the total number of apple slices? So now let's set up a new equation. Let's say we first started out with 30 apple slices in total. From 30, we're going to take a look at the number of apple slices that Russell has. So let x be the number of apple slices that Russell gets. And in this case, our outcome or output would be the number of leftover apple slices. And what you notice is that our function model would now become y equals 30 minus x. Now, what do we have here? We have our constant 30, also known as y-intercept, and then we have -1 as our slope. So let's go ahead and graph it. What do we notice? We notice that first of all, it is no longer direct variation because it has y-intercept that's not 0, right? Our y-intercept is 30 actually. And another thing is that we have our graph is no longer increasing. It's actually going down. It's decreasing. So now we know that when our coefficient is negative, coefficient becomes our slope value, right? So when our slope is negative, our graph is essentially decreasing. So now we know that when our slope is positive, our graph is increasing, and when our slope is negative, it's decreasing. Now, there's also instances where we get a flat line, right? And that's because our slope, remember, slope is a rate of change. Essentially, when our slope is 0, that means there is no rate of change, meaning our change is the same. There's no actual change happening. And what if when we get a vertical line, no longer a horizontal, not a horizontal line, but a vertical line, what happens? Like a cliff. Then what we would notice is that if you try to do vertical line testing on a vertical line, you'll see that these two lines just overlap, which means this does not pass the vertical line testing. So therefore, this is no longer a function, meaning our slope is undefined. To 3, 1 and 3, 5. And both points are on the equation x equals 3. What you would notice is that we would get 5 minus 1 over 3 minus 3. And we cannot divide a number by 0. And we can get into it next time, but essentially the reason why we can't divide a number by 0 is because, think about it, let's say you have 1 divided by 1. What you end up getting is 1. What about 1 divided by 0.1? You get 10. What about 1 divided by 0.01? You get 100. Then what if 1 divided by 0.00001? Then what you would end up getting is 10000, right? I think I got the number of zeros right. My point is, as our denominator gets smaller, if our numerator stays the same, stays constant, as our denominator gets smaller, our total value ends up becoming bigger and bigger, and therefore it would get infinitely bigger as our denominator approaches 0. So that's why we cannot technically divide a number by a 0.